All right, I wanted to finish up section 5.5 in this video. We're talking about a U substitution. And so far we've just been looking at several examples where we've had an indefinite integral. So I wanted to show you some now where we are working with a definite integral and there's also a U substitution going on. Let's take a look at this example. Suppose we want to integrate x times x squared plus 1, the quantity cubed, on the interval 0 to 2. Okay, well, if we set up a U substitution, we'll want to let U be x squared plus 1, du would be 2x dx, and I've got an x dx here. Divide both sides by 2, and a 1/2 would come out of my new integral involving U. Okay, now here's the thing. When you make a U substitution, everything about the new integral has to be in terms of the new variable U. That includes the bounds, okay? Because right now, the fact that we're going from 0 to 2, that's in terms of x. I wouldn't want to continue to write 0 to 2, because otherwise I'm mixing U and x, and you never want to mix the variables together, okay? X is going to go away completely in this, and so we've got to make sure we change the bounds. Now, if x is 0, the lower bound, U would be 1. So my lower bound is now going to be 1. If x is 2, 2 squared is 4 plus 1 is 5, U would be 5. Okay, so here's my new bounds, and now I can get the antiderivative. It's going to be U to the 4th over 4 times 1/2 is U to the 4th over 8, and we're evaluating that from 1 to 5. Make sure that you've got the evaluation bar. And now you can plug in the bounds. When you plug in 5 to the 4th is 625. 625 over 8, we're subtracting 1/8. That would give us 624 over 8, which would actually be 78 when you simplify that. Okay, so 78 would be my answer. Now, remember that when we have an indefinite integral and there's a U substitution, we have to substitute back. It's different with a definite integral. Okay, once you get your new integral in terms of U, x is gone and not going to come back. Okay, so consider that when you're working these. Here's another example. Okay, suppose that we want to integrate 1 divided by 3 minus 5x, the quantity squared, on the interval 1 to 2. Well, here'd be another U substitution situation. I'm going to let U be 3 minus 5x. du would be negative 5 dx, and if I divide both sides by negative 5, dx, which is in the numerator, is going to be replaced with negative 1/5 du. Negative 1/5 is a constant that can come out of my new integral here. Du, of course, would stay inside. And so inside my new integral, I'm going to have 1 over U squared du. Also, I have to change the bounds. So if x is 1, and you plug that into your substitution equation, U would be negative 2. Okay, that's going to be my lower bound. And then the upper bound, when x is 2, 3 minus 10 is negative 7. Okay, so I'm going from negative 2 to negative 7. Now, that doesn't make sense in terms of the bounds and how they should be. We know the smaller number is supposed to be the lower bound, the bigger number is supposed to be the upper bound. Well, we can easily fix that. If we switch the bounds and then throw a negative in front, then we have something that makes sense. Okay, negative 7 is the smaller number when you compare negative 7 and negative 2. So the lower bound is negative 7, the upper bound is negative 2. Now that looks good. Sometimes in a U substitution where you have to, switch the bounds, when you have to change the bounds, sometimes you then have to switch the bounds. It doesn't happen a lot, okay, but it is something to watch out for. Of course, make sure that your bounds make sense. Smaller number, lower bound, bigger number, upper bound. 1 over U squared is the same as U to the negative 2nd. And so now I can get my antiderivative. It's going to be U to the negative 1 divided by negative 1, which would be, and multiplied by 1/5. That'll give you negative 1 over 5U, and we're evaluating that from negative 7 to negative 2. Plug in the bounds, and you'll have 1/10 minus negative 1 over negative 35. Okay, so 1/10 minus 1 over 35, you should be getting 1 over 14 when you simplify that. Okay, and should go without saying by now, but you know, exact answers, of course. Okay, here's another one. Let's begin with a u substitution again. So in this one, if I were to let u be pi times t, du would be pi dt, so 1 over pi would come out of my new integral involving u. Change the bounds, because right now they're in terms of t. If t is 1/6, u would be pi over 6, and if t is 1/2, u would be pi over 2. Okay, pi over 2 is the bigger number compared to pi over 6. So now I need to get the antiderivative of cosecant u cotangent u. Well, that would be negative cosecant u, since the derivative of cosecant u is negative cosecant u cotangent u. We're evaluating this from pi over 6 to pi over 2, so now I can plug in the bounds. Okay. Cosecant of pi over 2 would be 1. Cosecant of pi over 2 would be the same as 1 over sine of pi over 2. Sine pi over 2 is 1. 1 over 1 is 1. And then cosecant of pi over 6, that would be 2, because cosecant of pi over 6 is the same as 1 over sine of pi over 6. Sine of pi over 6 is 1/2. 1 over 1/2 would be 2. 1 minus 2 is negative 1. Times negative 1 over pi, be 1 over pi is the answer on that one. Okay, here's another one. So, and by the way, I mean, there's really nothing new compared to what we've been doing other than just change the bounds. Okay, make sure that your new integral is entirely in terms of the new variable. In the case of a definite integral, that would be the mistake that I would see the most, is that a student won't switch the bounds and they'll be mixing u and x or u and theta or whatever it is. Okay, so make sure that you change the bounds on that new integral. Okay, here's another one. So this would be another u substitution situation. For this one, I'm going to let u be cosine theta. Du would be negative sine theta d theta, which I have in the numerator. It's going to be a negative coming out of my new integral involving u. And I've got to change the bounds. Now, I like to write down, you know, how we got the new bounds. You don't need to do that. Just make sure that you've changed the bounds, okay? Ideally, you know, the more that you do this, you shouldn't need to write down those, you know, how you're getting. You can do mental math and know what those new bounds are. But okay, so if theta is 0, and you plug that in here, cosine 0 is 1. So my lower bound is going to be 1. And if theta is pi over 6, cosine pi over 6 would be root 3 over 2. Now root 3 over 2 is smaller than 1. So I'll need to change the bounds. I'll need to switch them. Throw a negative in front. Okay, and that will get rid of the negative that's already there. And so now this looks good. Okay, I'm going from root 3 over 2 to 1. And I'm integrating 1 over u cubed, which would be the same as u to the negative third. I can use the reverse power rule on this. We're going to have u to the negative second divided by negative 2, or that'd be negative 1 over 2u squared. Evaluated from root 3 over 2 to 1. Okay, and plug in the bounds. When you plug in 1, you'll have negative 1/2 minus, we plug in the lower bound. Okay, root 3 over 2 squared would be 3/4. Times 2 would be 6 over 4. Okay, or that'd be 3/2. You're going to flip that. Negative 1/2 plus 2/3 would be 1/6. So 1/6 would be my answer on that one. Okay, here's another one. Go right to the answer. The answer is 0. How do I know that? Well, because of one of the properties that we saw earlier said that if you are integrating an odd function and the bounds are opposite numbers, you always get 0. That's because you've got two regions, one above the x-axis and one below the x-axis, and they're both the same size, and they're offsetting each other, going to give you 0. Okay. If I replace x with a negative x, that would be the same result as throwing a negative in front of the function. Okay, so the integrand would be an odd function, and the bounds are opposites. Now that's the reason why it can go to 0. Now if I were integrating this from let's say negative pi over 4 to pi over 3, then I can't go right to the answer then. In fact, that would be an integral that we wouldn't know how to do. Okay. So there's some key things that need to happen there. But, you know, the point of that is to say don't forget about the things that we've already talked about. Okay. We do still need to know that. Okay, here's another example. Let's integrate the function 1 over the square root of 1 minus 4x squared on the interval 0 to 1/4. Okay, well, now, if I were to let u be, well, actually, before I do that, so 4x squared, that's the same as 2x, the quantity squared. And why I would want to look at it like that is because I know that the derivative of sine inverse of x is 1 over the square root of 1 minus x squared. Now, I don't have 1 over the square root of 1 minus x squared. I've got 1 over the square root of 1 minus 4x squared. Okay, but that very much resembles what I already know about the derivative of sine inverse of x. Okay, and I've mentioned many times now. We still have to make sure that we're knowledgeable with our rules for differentiation. Okay, so now if I let u be 2x, du would be 2 dx, a 1/2 would come out of my new integral involving u, and when I change the bounds, okay, if x is 0, u would be 0. If x is 1/4, 2 times 1/4 is 1/2. Okay, but now I'm looking at something that will allow me to just go to the antiderivative in terms of u. I know that the derivative of sine inverse of u would be 1 over the square root of 1 minus u squared, since I already knew earlier the derivative of sine inverse of x is 1 over the square root of 1 minus x squared. Okay, it's just I needed a little substitution to have this work out for me here. And now I can plug in my bounds. So when I plug in 1/2, sine inverse of 1/2 is pi over 6, because sine of pi over 6 gives you 1/2. When I plug in 0, sine inverse of 0 is 0, because sine of 0 is 0. Pi over 12 is the answer there. Okay, here's one more problem just to make sure that we're paying attention to things when we're writing this stuff down. Find the error. Well, okay, so ignore what's written in red there, but if I had the integral for sine x cosine x dx, that would be the same as the integral for cosine x times sine x dx, right? Multiplication is commutative. I can flip those and there's no problem. Now, if I use a u substitution on both of these, if I were to let u be sine x, du would be cosine x dx, and I've got a cosine x dx, right? So on the left, I'm going to have the integral for u du. Now, what if I were to make a u substitution over here, although I'm going to call this w, since I already used u. Same idea, though. Okay, what if I let w be cosine x? dw would be negative sine x dx. And I've got a sine x dx. A negative would come out of my new integral involving w. Okay, now if I get the antiderivative, reverse power rule, you're going to have u squared over 2, and then negative w squared over 2. U is sine x, w is cosine x. So I've replaced those. Add the expression on the right over to the left. And if you multiply throughout by 2, you end up getting sine squared x plus cosine squared x equals 0. But hold on, sine squared x plus cosine squared x is 1, right? For all x, that's the identity that you would see in trig. That's when, you know, our Pythagorean identity, one of them. Well, the error would be the plus c, right? Now there'd be two constants here, so I'm calling this c1 and c2. But that'd be the mistake about, you know, why this is not 1. Is because the student forgot to add the constant there. So that's something that, you know, I've mentioned a lot. Make sure that you add the constant at the very end, that plus c. Otherwise, you will lose points. Okay. In some cases, it matters as far as getting the right or wrong answer. And of course, you're not finding a general antiderivative then if you don't have the plus c there. Okay. Now, of course, in this problem, we already know that c is 1. Okay. Yeah. That's all I had in this section. Now, the homework in section 5.5 is on page 418. Be sure to look at the odd numbered problems that are listed there. And I also wanted you guys to look at some of these odd numbered problems that are on page 422. The review section is at the end of the chapter. The reason why I'm wanting you guys to look at some more problems here in the review is because a lot of the problems that I saw were in the review involved a U substitution, okay? And it's a good idea to make sure that you're definitely comfortable with the U substitution, especially if you have plans, you know, to go forward and take Calc 2. So be sure to look at those, and of course, the more practice, the better, okay? But at this point, we are now done with Chapter 5. And I'll plan to get into Chapter 6. Chapter 6 is going to be the last chapter that we'll be doing for the course.